This is the second part of the osmosis video. In the first part, we showed a video of osmosis occurring and that introduced the term osmotic pressure. And osmotic pressure is assigned by the pi symbol. And it simply is typically a measure of height. That's where the units of millimeters of mercury comes from. And it occurs because I have a semi-permeable membrane. That means that some things go through and other things don't. So these large sucralose or glucose molecules here go through the membrane. Do not go through the membrane. And the smaller water molecules do go through the membrane. So basically this is before equilibrium, but it has already started. So here's my glucose solution. It's already climbing. And at some point in time, it will stop to climb. And that means it's at equilibrium, which means that now the water is flowing in both directions equally. Here you see that for every 4 arrows I have going up, I only have one coming down from the glucose solution. And when I go to equilibrium, then I have 3 going down and 3 going up. So that's what it means at equilibrium. The other thing that I want to point out before I do the problem is just to know that the formula that's given is that pi is molarity RT, but you can also use PV is equal to nRT, the ideal gas law, but this one is not given. And so I'm going to show you both ways to do that in the next problem. So the problem that I have is this. Okay, I'm going to start this problem as I typically do. I have a mass of 7.480 grams. I have a volume of 300.0 milliliters. I have an osmotic pressure, so pi is 1.43 atmospheres, and I have a temperature of 27 degrees C. And it wants to know, it's also important to know where you're going, is what the molar mass is. Okay? And so, like I said, I'm going to show you the first time how to do it using the formula that's going to be given to you. And that formula is pi is equal to mRT. R is that gas constant we used in chapter 5. Okay, so 0.0821, and that's liter atmospheres per mole K. And because of these units, my volume has to be in liters. Okay, so that's from chapter 1. So that's going to be divide by 1,000, move the decimal place 3 to the left, however you want to think about it. It's 0.300 liters. The atmospheres it's already in, moles is fine, and Kelvin. And so this is to go to Kelvin. We did this more in chapter 5 than we did in chapter 1. I add 273 to give me 300 K. Okay, so when I look at this, I have my osmotic pressure. I have R because it's a constant. I have temperature, so I'm going to be solving for molarity. Okay, so I have 1.43 atmospheres is equal to my molarity times 0.0821 times 300. So I get, nothing happens on the left, 1.43. When I multiply these two terms together, I get 24.63 M. And to isolate M, I divide both sides by the 24.63, so I have 1.43 divided by 24.63 is equal to M. And so my M is going to be 0.05806 molar. Okay? Now, molar is not what I'm trying to get to. M is not the same thing as molar mass. Molarity is not the same thing. So I have to think, okay, well, what's the formula for molarity? So this is not given to you because it was also from last semester, that molarity is moles over volume. Okay, and we did do that earlier in this chapter. All right, so I have my molarity, I have a volume, so I'm going to solve for moles. So I have 0.05806 is equal to N over my volume is in liters of 0.300 liters. Okay, and so I'm going to multiply both sides by the 0.3. So I have 0.05806 times 0.300 is equal to N. So N ends up being 0.01742 moles. Again, moles is not what I'm looking for. I'm looking for molar mass. So I have to think about what could be the formula for the moles. And the one I'm going to be using is that moles is mass divided by molar mass. Okay. And so I have 0.01742 is my mass, is 7.480 divided by my molar mass. So I'm looking for molar mass, okay? And so the first thing when my unknown is on the bottom is to multiply both sides by the bottom. So it's 0.01742 molar mass is equal to 7.480. So molar mass is going to be 7.480 divided by 0.01742. And that gives me 429.4. And the answer for molar mass is grams per mole. Okay? Oops. And so that is my overall answer. Okay, so that's using it with the formula that's given. I'm going to do the same thing, except for I'm going to use the ideal gas law. And so I don't have room on the slide, so I need to erase a whole bunch of stuff. So I'm going to just erase everything but what was given, so I don't have to start completely over from scratch, although it may be just as fast to do that. Okay. I'm lucky in the fact that as long as I touch as long as I don't let up, it erases the whole thing. I don't have to hit every single part of the thing. So like the whole circle went away together. But what I miss is things like dots. Okay. So using the other formula, I'm going to use PV is equal to nRT. So I still need R. Temperature still has to be in Kelvin. My volume has to be in liters. My pressure, though, this time, remember that this is a pressure, okay? So when I start filling in, I have 1.43 times I have a volume of 0.300. N is what I don't know, and R is 0.0821, and temperature is 300. So remember when you're doing these, you must have something that's unknown, okay? And when I do that, the left-hand side, when I multiply these two things together, I get 0.429. And when I do the right side, it's the same on the right side, so I still get 24.63 N. I divide both sides by the 24.63, so 0.0429 divided by 24.63 is equal to N. N then is still going to be that 0.01742 moles, which is what we got last time for N. Okay. And then again, N is equal to mass divided by molar mass. I have moles, I just found it. I have mass, and I want to find molar mass. So I have 0.01742. So the last step is exactly the same, 7.480 divided by molar mass. I multiply both sides by the molar mass. I get 0.01742 molar mass. And please do not round too much, okay? You'll get the wrong answer, and I will take off a point. Okay, and then molar mass is going to be the 7.7480 divided by 0.01742. And so my molar mass is the same answer as I got before, 429.4, and the units is grams per mole. Okay, and so that's how you can do that problem. That's the only example I have. We'll work more in